everyone, welcome to me and Ethan's talk on a glide, skip, or a jump, efficiently stream data into your Medallion architecture with Apache Hudi. The Medallion architecture provides a systematic methodology for structuring and enhancing data within a lakehouse, facilitating a smooth transition of raw data sets into actionable insights. By embracing this layered structure, which categorizes data from bronze, silver, and gold stages, raw data is methodically processed, evolving into a purified and augmented asset ready for in-depth analysis. Now, while several implementation techniques exist for the Medallion architecture, this presentation will first delve into a more widely adopted conventional method. Subsequently, we'll explore a more streamlined approach highlighting its unique benefits and advantages. I'm Nadine, and I'm leading OneHouse's developer initiatives, and I'm also an Apache Hudi contributor. I'm passionate about bridging engineering, product, and marketing to help drive developer adoption. Prior to OneHouse, I was at Rockset leading their developer initiatives, and prior to that, I was on Bose working on the Bose AR team. And today, I'm sharing the stage with Ethan. So Ethan, do you want to go ahead and give an intro?
Yeah. Hi, everyone. I'm Ethan. I'm a software engineer at OneHouse, working on core components of Apache Hudi and the foundation of our Lakehouse product. I'm a PMC member of Apache Hudi. Previously, I was working on data and networking. I built the first kind of incremental pipelines to power the near real-time network KPI dashboard at global scale.
So if you're enjoying the talk, we would love to hear from you. You can tag and follow OneHouse HQ with a sentence or two, and maybe have a screenshot of what you enjoyed about the session. Also, or you can tag and follow the Apache Hudi handle on Twitter with what you like or screenshot. The QR code linked is the link to the Hudi Slack community. Me and Ethan are active on the Slack community, so if you want to follow up async, you can find us there. And we're also giving away 10 Hudi hoodies, so if you want to tag and follow us either on Twitter or on LinkedIn, you'll kind of earn some cute hoodie, so that'll be great, and we hope to see you at booth 414, and it's right next where they're making all the custom lattes and stuff like that. So for the agenda today, we'll have an overview of the Medallion architecture and the Apache Hudi platform. Next, we'll cover the incremental framework with the CDC feature and how you can achieve fast updates and merges with the record level index. Finally, we'll do a walkthrough on how you can build a customer 360 app, harnessing the incremental processing framework with the record level index in Apache Hudi. So without further ado, let's get started with the Medallion architecture. With a show of hands, how many of you have heard or are familiar with the Medallion architecture? Cool, so a few of us. And so if you're familiar, you probably have seen a diagram that looks something like this. Right, and so we're going to do a quick walkthrough of what this is for those of you who may not be aware. When data is ingested, it's first unprocessed and stored in the data lake. And typically the raw layer or bronze layer, you'll have data duplication, change logs, event data, and more. And data typically here is unstructured. From there, data will graduate into a silver layer where you'll perform data deduplication. You'll validate the data, you'll have some sort of data management services running, and so much more. And then finally, you might write some join queries where you might join silver tables, and you might create a fact table or a gold table that can be used by AI, ML applications, analytics, and more. But this architecture, if you look at it, seems pretty easy to write. You're just graduating data until it's finally processed and used. But what does it really take to build the Medallion architecture? Well, it kind of looks something like this. And this is actually a true approach of several lead data engineers and companies that I've talked with. So we're going to walk through what this approach looks like. First, you'll ingest raw, unprocessed data into the data lake. And you'll create a raw or bronze layer. And I'll typically use raw or bronze layer interchangeably here. From there, you'll do a full table scan and grab all the data, including new updates and deletes, and you'll rewrite the table located in the silver layer with augmented data. In this process, you might use SQL or PySpark or something else to perform data deduplication, have some sort of data management services like file sizing, cleaning, and more. And augmenting the data with the examples I have given is actually a very manual process, because you have to manage and orchestrate these processes to ensure there's no concurrency or write conflicts that can lead to potentially, data loss, corruption, deadlock, and so much more. After you've done that, in order to create the goal table, you'll have to do another full table scan. And then from there, you might create a temp table where you're actually performing a join operations. And here, you might join several of these silver tables. And then you'll output it to some Parquet file, and then you'll do a complete table rewrite in a table located in the gold layer. On the query engine side, you'll have to do another full table scan to execute the query and return the results that can be later used for some downstream applications or tables and analytics. But you can kind of see here that there's kind of a general theme that's going on here. And some of it is doing full table scans, full table rewrites. And this whole architecture is a very manual process where you have to manually file size, clean the data, and so much more. And you have to orchestrate all these services. And the technology is currently available in the market. The majority of them kind of encourage this approach with the Medallion architecture because they lack a few key things. And so we're going to cover what these things are in this slide here. So you'll see you have the raw zone, silver zone, and gold zone. And each of these zones have the same services and features listed here. And so we're going to cover what those are. One of the things that some technologies don't offer is a fully automated table service that can help automatically manage, orchestrate your data to kind of maintain your table's health. For example, in Spark, you might have to run manual compaction where you have to merge smaller files to larger ones. And then also you might want to clean your data to ensure you have faster analytics and you're in compliance, right? But if you wanted to run these two services together at some point, right, which is typically what you would do if you're in prod, you have to implement your own optimistic concurrency control mechanism in Spark. And here, if two services are trying to modify a record, one would have to fail a reblock until the other service has completed its task. So the other thing I want to talk about is the incremental framework and indexes. The incremental architecture prides itself on incrementally updating data sets without having to reprocess the entire data over and over again. A key capability that achieves the incremental processing framework is being able to handle data mutations at record level. This helps avoid reprocessing non-changing data. So also, adding an indexing mechanism can further help quickly handle these record mutations because indexing helps locate records in the data lake faster and more efficiently. So by not having any of these table services and features and things like that, you have full table scans, full table rewrites, and much of the data management side is very automated. And at small data sets, you might not see anything and it might not be a problem. When you start getting to terabytes, petabytes, and exabyte range, this becomes unbearable. And the only way you solve the problem is throwing more compute at it. And at some point, that's not even efficient, right? Because it becomes too costly. But what about if you can simplify the Medallion architecture? What's a probable way that this will look like? Well, one way you can do this is implementing Hudi into your Medallion architecture. And we'll talk about how this is efficient throughout the rest of this presentation. So typically in this architecture, you'll have some sources and you'll adjust data into the raw data layer or bronze layer, right? And that's pretty straightforward. But then from there, if you want to update your silver layer, right, you can incrementally pull the changes that are coming in from the bronze layer and do row-level updates to the silver layer. On this end, Hudi has a way to automate these several services so you don't have to manually handle file sizing, cleaning, clustering, and so much more. And so you reduce this operational overhead that you would typically have to do if you're working in Spark. From there, if you wanted to join several of these silver tables, you'll still have to create a temp table where you perform the join operation. But any new data comes in as a result of the join, you can incrementally update your gold tables with just those changes. And on the query side, you can do efficient lookups to grab the data that can be used for analytics or applications. So I kind of introduced Hudi into this architecture, but this leads into the Apache Hudi overview and what it provides and how it affects the Medallion architecture, which brings us to the overview here. So previously, we looked at the bottlenecks of the Medallion architecture, but what about if we flipped it? What about if you had these features and services enabled? Well, Apache Hudi is a data lakehouse platform that provides database-like features and services to your data lake. With Hudi, you can fully automate these table services that continuously schedules and orchestrates clustering, compaction, cleaning, file sizing, indexing, and so much more, to ensure that your tables are always ready and they're kind of healthy in that sense. In addition, you can replace old school batch pipelines with the incremental processing framework. Hudi also allows for quick updates and deletes with a fast pluggable indexing. And this includes full streaming workloads, including out-of-order data, bursty writes, and data deduplication. Since Hudi provides an indexing mechanism, you can take the data updates from your upstream databases and apply the role-level changes to your downstream applications. And as a result of the incremental framework, you have faster ingestion, faster processing times, which leads to faster analytics. So Hudi's features and services enable you to build performant applications, bringing down your analytics that you typically would do for hours and days down to minutes. So let's get a bird's eye view of what this platform looks like. So we typically hear table formats everywhere, but actually Hudi is a step level ahead of that, and it's a full-blown platform. It's a comprehensive platform designed for data ingestion and processing. And it's equipped with a range of features aimed at maximizing the efficiency of both writes and reads. So at the foundational platform, you have your data lake storage like HDFS, S3, and this is where your data resides. And it might be in formats like Parquet or Avro and so on. And I think this is pretty straightforward. But above that, you get into the transactional database layer. This is where Hudi's true power shines. It offers multiple table services like indexing, concurrency control mechanisms, and others. And it offers a significant enhancements to data and table management. You can think of Hudi as like giving your data lake like superhero capabilities. If you think of a data lake, like you can think of it like throwing clothes on the floor that's disorganized, and if you're trying to find a pants that you fit in 10 years ago, good luck. But Hudi provides a way to organize this in a way that you can efficiently find it and use it for some sort of use case, right? So after data has been successfully ingested and managed, now you have this like kind of execution layer. Here, Hudi allows this interoperable query engine layer where you can query data with popular query engines like Trino, Presto, and Athena. And that's pretty cool. So by facilitating these integration, Hudi allows for advanced querying of data. But now we have this bird's eye view of what Hudi looks like, but now we're gonna double click into what the file layout, Hudi's file layout looks like and why it's important. And this slide is important because when we get to the record level index, some of these terminologies will be used, so I'll go over it over here so it's easy to understand. So Hudi table consists of file slices, and each slice contains a base file, which is basically a .parquet file produced at some certain commit or action time, right? And alongside it, there are log files, which is in a .log format that contains inserts or updates since the base file was created. And a group of file slices is known as a file group. Now, when a write comes in, the records are written to the file slices, and each record has a key that is mapped to a particular file group. So and there are a couple of advantages with this, the way that Hudi has its file layout. Now on the right side, if you're writing to a Hudi table and you have multiple table services running, which you would if you're in prod, right? Alongside with the ingestion, the services don't block each other because Hudi has a multi-version concurrency control mechanism. Now on the read side, from the point of querying a Hudi table, the file layout facilitates the query engine to be able to query data at a particular point in time. And when you get into an incremental framework, this becomes really important. Now on the bottom half, when a record gets written to a file group, Hudi's timeline also records when that commit or action is done in the timeline. And the timeline is located in the .hudi folder, and it's essentially an event log. And there are different actions and stuff that can be recorded in the timeline, such as when clustering happens or when compaction happens. And a key thing to point out is that whenever there's a commit or action, there's a timestamp associated with that action. After the timeline, there is the metadata table, and this is also really important. The metadata table is different from the timeline structurally in a sense that it's an internal merge on read table. The metadata table stores like basically, the metadata table is where each partition stores information about the metadata in the file. For example, column stats partition will store information about the column min-max values, whether there were null values, and so on. And the metadata table also stores file partitions, which stores information about where files are located within which partition. So the metadata table is essentially a central place for all the metadata. For example, when a write occurs to a Hudi table, automatically the footer of each file might be populated with a Bloom index. Additionally, the metadata table also stores the Bloom index from all the files. So instead of opening and closing the files to check whether a record may exist in this file group, Hudi can just check the metadata table and save on this file I/O cost. And when commits happen, the metadata table also gets equally updated. So you can think of the metadata table as this like big indexing table that allows you to efficiently find things and update records as well. So when you create an index for existing data, whenever new updates arrive, the index has to be updated as well, which means like the metadata table. The other thing that's important to know is that Hudi actually stores state. So in the last slide, we talked about the timeline, and we also talked about the metadata table. So if a record has an update, Hudi checks the record's keys to see if a record exists in a file group. And if it does the update of that particular file slice depending on where it's located. Equally, the timeline and the metadata table also get updated as well. And since Hudi maintains a timeline of when actions occur and when writes occur on a Hudi table, you can essentially find out what changes occurred in that time range. Because as I mentioned earlier in the timeline, whenever a commit or action happens, there's a timestamp associated with it. So when you want to update downstream application or tables with just the data changes, you can use Hudi's incremental framework with the CDC features to do the updates. So Hudi is actually proven on massive scale. And before we double click into the incremental framework with the CDC feature, we're going to talk about how it's doing that. ByteDance with TikTok, Uber, Walmart, GE, they all use Hudi for mission critical applications. And I think one of the most notable things that I've seen is at ByteDance, Hudi's being used at exabyte scale where a single table is at exabyte scale, and even at this level, Hudi's able to bring down analytics from hours to minutes. But one of the ways it's able to bring down analytics is through its incremental framework with the CDC feature that we're introducing. And in the next section, we're going to talk about that. So I'll pass it to Ethan to talk about the incremental framework with the CDC feature.
So to recap, within the Medallion architecture, we presented this straightforward and more simplistic approach to constructing your bronze, silver, and gold tables. So a standout feature that spares you from the full table scans is Hudi's incremental framework. So by using this framework, only the changes are streamed to update the downstream tables. So to realize this end-to-end incremental processing, Hudi provides the Hudi streamer to efficiently pull the changes from the source, support mutable data and record level updates, and completely read the data to the downstream sink, all the way from the source to bronze, silver, and gold tables. So here is an example of how you can use Hudi streamer to construct the incremental processing end-to-end. So a common use case is streaming the change logs from a database like PostgreSQL through DBZM and Kafka. So each message from the Kafka source has the before-after images reflecting the changes. So the schema is registered to the schema registry. In the first step, Hudi streamer gets the new data from the last checkpoint from the Kafka source and bulk insert them to the bronze table. So this bronze table contains the exact raw events from the Kafka source for further processing. So next, another Hudi streamer is constructed to do any kind of data cleaning and augmentation. So for example, user can transform their data by flipping the fields, selecting relevant fields for projection, or they can do any kind of custom transformation. So once that's done, the data is upserted to the silver table, which is a clean data set. Once new changes are landed in the silver table, the subsequent Hudi streamer job conducts a more complex operations with the business logic. using the C code provided by the user. So for example, user can do the joining of the input with dimension tables or other data from multiple tables. So in this way, complex business logic can be applied on the changes. And then after that, the records are upserted to the Go table, which is like a summary table, which are ready for data analytics. So one key functionality here is supporting the mutable data in the incremental processing. So let's take a deeper look at how Hudi takes the changes and handle mutation and then stream to the downstreams. So when we look at this incremental processing from Hudi under the hood, there are quite a few steps between taking the incremental changes from source and streaming them from Hudi to the downstream. So to enable mutable data at the record level, Hudi provides the built-in support on locating the records and the record payload and merging API so that user can customize their insert, update, and delete. So as mentioned by Nadine earlier in the talk, Hudi needs to make sure that there's a consistency between the index, metadata, and data. And Hudi provides the automatic metadata management so that Hudi's timeline and metadata table is in sync with the data table. Besides managing the data and metadata, Hudi automatically optimizes the data layout on storage with small file handling and table services like compaction and clustering. So that query engines can read well-sized files and then improve the performance. So alongside the incremental processing, there could be multiple concurrent writers. For example, a user may want to backfill the table with older partitions, or they want to delete selected data for a particular user. So in that way, Hudi provides optimistic concurrency control and a multi-version concurrency control so that for different use cases, all of these cases can be efficiently handled. Now, you may wonder how Hudi handles the record level mutation, which is the most important part in the incremental processing. So Hudi provides the payload and merge API for updates, inserts, updates, and deletes. So user can customize what they need. So let's take a look at an example in this slide. So let's say we have a table that stores the bank accounts, and each entry has the UUID, the name of the account, the last updated timestamp, and the balance. So just like other databases, Hudi requires the primary key field to be specified by the user so that Hudi can identify unique records. And in this case, the primary key field is the UUID field. So for each incoming data batches, Hudi looks at the primary key to identify whether the input record is an insert, update, or delete. So let's take a look at this particular batch. So the first entry is the insert. Second entry is the update. So once Hudi conducts the upsert operation, the table is updated by inserting the first record and updating the record with UID 1. So similarly, for the second batch, we can see that the first entry is marked as delete. Second entry is another update, which is on my account. So once Hudi applies the upsert operation, it deletes the record. So now if you look at this end state of the table, you may notice that even after this second upsert operation, the balance for my account is not updated. This is because we want to honor the balance of the latest timestamp. So in this case, Hudi looks at the ordering field, which is the TS field here, so that the incoming data or incoming entry is actually like late arriving data. So it shouldn't actually update the value in the table. So Hudi has built-in support for the event time ordering, which is pretty prevalent in streaming and incremental processing. And in this case, it makes sure that I don't get some $20 from nowhere. So once the data mutation is done, Hudi attaches the metadata such as commit time and file name to each record and also updates the Hudi timeline. so that Hudi timeline has the full history of what's going on of the table. And this essentially serves as a state for streaming changes from this Hudi table to downstreams. And as I already mentioned, for record level mutation, the record key field is required. However, for some use cases like event log ingestion, which only requires inserts, Hudi supports the automatic primary key generation, so that user doesn't have to specify the primary key. So this new feature is in the upcoming Hudi 0.14 release for improving the user experience. Aside from the existing incremental pools, Hudi provides a new CDC mode for incremental processing. So these provide a Debezium-like change logs with before and after images. Here is an example to show how it can be read in the Spark data source and what its output looks like. So for inserts, the before image is now, and after image is the insert value. For updates, the before and after images show the values before and after the change. And for deletes, the before image is the record to delete, and the after image is empty. So through this new CDC feature in Hudi's incremental processing, user can do further transformation or processing based on both the before and after images. So as we discussed the record level mutation, one requirement even before this happens is how to locate the records. So next I'll talk about how Hudi speeds up the upsert operation through advanced indexing and the new record level index. So indexing is actually like a known technology. So it's widely employed in database systems like RDBMS and data warehouses to locate information pretty quickly. So this is similar to how index page at the end of a book to help you quickly locate the information you want to see with the page numbers. So in data system, such indexes can reduce the I/O cost and commonly used to improve the query performance. Hudi also uses the indexes to locate record efficiently and do fast upserts. And as you can see in this diagram, this shows how Hudi actually leverage index to reduce the I/O. So on the right side, without the index, each file has to be merged against all the updates and deletes from the input, so that it's pretty expensive. With index, the updates and deletes are first located for each file, so that each file only has to be merged with the updates and deletes for that particular file. So this significantly reduces the I/O overall for merging the data. And Hudi already supports different indexes for different use cases. So on this slide, I show two popular kind of use cases. The first one is updating the dimension table with user input. Usually, this generates a lot of random updates across most of the files in the table. In this case, simple index is the best because it simply reads the key and location from the table, and it incurs very little overhead. For the second use case on the bottom, it's like some input events ordered by timestamp, because user generates some logs or events from their latest actions, and most of the events fall into the last few hours. So only a small portion of the files are going to be updated in the whole file. So in this case, we design another index called Bloom index, which is better for these kind of late arriving updates for dedupe. So what Bloom index does is uses the Bloom filters co-located with the data files, which has very low storage footprint, to prune the files first by filtering out the data files that are irrelevant. And these avoid reading all the keys from all the files. So this can significantly reduce the I/O if only a small portion of data files are going to be updated. So for large-scale data sets ranging from tens of terabytes or petabytes, this simple Bloom index may still not be performant enough. So that's where H-based index comes into play. So it is used to send the key lookup to the external H-based table, storing this key to location mapping, so that this key lookup can be blazingly fast because the H-based server already caches the information, so it can serve the content pretty fast. And as we can already see, there are a couple of challenges, even for large datasets, for using existing indices. As already mentioned, for both Bloom and simple index, they need to read either the keys or Bloom filters from all the files. So in this case, they have to read some data per file. And this can be really expensive for large datasets with many files, particularly on cloud storage, because cloud storage enforces the relimiting on I/O, which means that you can only send a certain amount of RPC calls to cloud storage to get the data. And this creates a bottleneck to the indexing phase, especially when the table has so many data files. And for H-based index, although it's pretty performant for larger data set, a separate H-based server has to be maintained. And H-based is known for operationally difficult to maintain and scale for throughput, because that requires dedicated resources and expertise for tuning all of these different configs in H-based. So now the question is, can we design a new index to address both challenges? So that's where recurrent index comes into play and to address these challenges. So by design, we make the record level index to store the key to location mappings, just like H-based index. But instead, we store the information directly in the table level metadata. So to realize that, we create a new partition called record index directly internally in the metadata table to store the mapping and the index metadata. And this data is laid out in a few file groups instead of co-locating with other data files, so that it can drastically cut the cost of file I/O. To make the storage footprint pretty low, we design an efficient key to location entry, so that a combination of random UUID and daystream partition only takes 50 to 55 bytes. And to make sure record level index has fast index update and lookup performance, we directly leverage the existing Hudi metadata table. So the metadata table is essentially an internal MR table, which provides uniformly fast updates for different index metadata. And the H-file format, which is best for point lookup, is used by metadata table as well, so that for any key lookup, we don't have to scan the whole file, but just doing like a few scans to get the results. So now let's look at how record level index metadata is organized on storage and how read and write works. So as already mentioned, the record level index is stored in the record index partition in metadata table with multiple file groups, just like a normal Hudi table. And each file group contains multiple file sizes, and the latest file size reflects the latest snapshot. So given that metadata table uses H-file, so the H-file in this case contains the key to value pairs of the record key to location mapping. So let's say we have a set of record keys to look up. So the first step is we use the hash function to identify the file group that stores these keys. And then we use point lookups without having to scan the whole file to actually locate, to get the information for these record keys. And for updating the record level index, the metadata table internally writes new log files, just like this, and uses the same log format, and which each data block using the same H-file format as well. So during the lookup, in this case, both the base and log files are read to scan the actual record keys to be looked up. And to make sure the read performance on metadata table is better, it does the periodic compaction to merge the base and log files into a single H file so that the performance is good. So now let's look at how RLI can improve the performance and unlocks different use cases. So we have done a few performance benchmarks on both read and write to demonstrate the benefit. So in the first case, we have like 1 terabyte data set, and each write batch has around 200 megabytes of random updates across the table. So this is around like 0.02% of updates. And we compare the performance of record level index with the global simple index, which is the best for random updates. So as you can see in the charts, the index lookup latency is reduced from around 20 minutes to just 1 minute after using record level index. So this is because RLI only has to read the metadata from a few file groups instead of all the files, which is done by the global simple index. So overall, this contributes to 2x improvement on the overall write latency, as the savings from the index lookup offsets the kind of small additional overhead of updating record level index in the write stage. So next, we also tried the RLI, how RLI can improve SQL latency with point lookups. So we used the store sales table in the TBCDS 10 TB datasets, and we ran 2 types of queries. One is the select star for a particular record key, and the other is delete operation on a particular record key. So by applying record level index on the filtering, we see 2 to 3x performance improvement with record level index compared to no RLI. This shows up how record level index can really unlock great SQL performance as well in this case. So we are releasing the record level index in the upcoming Hudi 0.14 release, and we really love users to give it a try and then give us feedback. So next, I'll hand it off to Nadine to talk about a case study in the Medallion architecture with Hudi incremental processing.
So we're going to talk about how you can build a customer 360 app using the Medallion architecture with Apache Hudi. So this is kind of what the architecture looks like, and we're going to take it section by section on how you can implement it. So the first section that we'll do is that you'll have first like people signing up for an account if you're building a customer 360 app. You might have some like clickstream app activity with users making purchases. You might have some cart activities. You might have them clicking on certain links and so on. So basically, if you're using a transactional database, you might bulk insert that. And if you're having some activity, you'll probably push it to Kafka and then bulk insert it into the raw layer. And this is a sample schema of what this can look like. So you have a clickstream schema. You might have a click ID, a timestamp, the URL that they clicked on, and so on. The purchase schema might look something like this. You have the purchase ID, the customer ID, the quantity they want to buy, the purchase date, and more. Then you have the cart activity, which might have an activity ID, a product ID, a customer ID, the activity type, whether they added or removed from cart, the quantity, and then status, whether the cart is abandoned or not. And then from there, once you have all the schemas, any new changes that happen on the bronze layer on the raw data set, you can pull just those incremental changes with just those updates and deletes using the incremental pull with the CDC feature, and only do row-level updates on your silver tables. And so that's really cool. And then from there, if you wanted to update the gold layer, you'll still create a temp table where you might join several of these tables to understand what's going on with the user, and then use an incremental pull with CDC to update the gold tables with any of those changes. And if you wanted to write a join, it might look something like that. So a join can look like, you might have the customer's information, the URL they clicked on, if you wanted to correlate users' activities with purchases. You might have the product ID, purchase date, and whatever fields you're interested in. And then you might join like you might collect it from the customer table. From there, you might do like a left join on the clickstream table based on the customer ID, and you also will probably do a left join on the purchases table based on the customer ID. And then if you wanted to filter on some sort of time range, you can do that with the where clause, and then you can order by whatever field you're interested in this case, ordering by the timestamp, the purchase date, and then the last name. And so once you get those results, you'll incrementally update your gold tables, the tables located in the gold layer. And then on the query engine, you could do an efficient lookup to just pull those changes and then power your analytics or other applications. So this wraps up the walkthrough. This is the road level map of what's coming up in Hudi. So we have a 14th release coming pretty soon, which will introduce the record level index, which we just talked about. We also have auto-generated keys for use cases without user providing a primary key field, so that's really cool. And then we have a new MR reader in Spark to boost query performance. A portion of us are also working on the Hudi 1.x release, which is super cool. And one of the things that it's going to be really big is bringing like database capabilities to your data lake, which is super new. The store format changes will change, which will unlock long retention of the timeline, non-blocking concurrency and control, which is also really cool. And then we have enhancements to indexing, performance for better abstractions, APIs for engine integrations, and more. So the 1.x release will be a big release that will hopefully be coming up towards the end of the year. If you're interested in learning more about Hudi, you can scan the QR code to join the Slack. And if you like and use Hudi, please give us a star on GitHub. And also, you can check out the Apache Hudi handle on Twitter. And also, you can check out the OneHouse HQ handle on LinkedIn. Me and Ethan are active on the community Slack. We'll also be here for questions, and you can find us after the session on booth 414 if you have more questions about Apache Hudi. We want to thank you for joining our talk. We hope you enjoyed it. We hope you enjoyed it. And please give us a shout out on LinkedIn or Twitter. Thank you.